When you study optimization, which is really a mix of mathematics, some sort of heuristics and a lot of other things, it is art, science and mathematics of choosing the best from a given set of alternatives. Best, what is the meaning of best is defined by the user. So, convexity is a central theme in optimization. Without convexity, there would be no optimization, no modern optimization. And today we are going to talk about convex sets. So, we are going to talk about, so what is important, see the link is this. So, this is convex, there is a subject called convex analysis, which deals with the analysis of or the properties of convex sets and convex functions. Convex functions will come the next day, next class. So, and this convex analysis has huge implications, huge effects in several parts of mathematics. An important area where it is applied is PDE, partial differential equation. But the most important area which feeds this subject and this subject feeds this is optimization. There are many areas in which convex analysis comes into the fore, but optimization is where it is absolutely central. Without a knowledge of convex sets and convex function, any understanding of modern optimization makes no sense. Okay. So, we are going to talk about convex sets. So, here our space of working is Rn. Here our space of working is Rn, n dimensional space. I think most of you know this because, so Rn is a space where every point is characterized by n real numbers. So, if you have Z in Rn, then this, so Z is a vector actually, is given in, so the n real numbers which are depicting this point, and each of these numbers xi is an element of the real number set. So, prototypical example is the Cartesian coordinate plane, which you know from your high school days, the two dimensional plane. So, any point that you take here can be expressed in two numbers, the x coordinate and y coordinate. So, then when you are talking about Rn, then you have x1 coordinate, y1 coordinate, x2 coordinate, x3 coordinate, x4 coordinate, xn coordinate. You can think in that way. Of course, there is no geometric vision after third dimension, but that is where the algebraic manipulation becomes important, that you are talking about geometry, but through an algebraic language. So, here this is the vector which denotes this point x1, x2. So, if you change any one of them, so if I make this to be 0, x1 to be 0 and keep x2 or I keep make x2 to be 0, keep x1 as same. So, basically this will now represent this point, and then this will be the vector which will represent this point. So, you see the direction and magnitude both changes once we change any of these coordinates. So, these coordinates are representing vectors, geometrical vectors, and hence these, when you write it in this more general setup, this is also actually representing vectors. So, these are vectors in n dimensional space. Now, this course or any course in optimization demands the knowledge of two things from you. One is linear algebra. Linear algebra is central to all mathematics, of course, but anyway, it is central to these two. And then you also need to know multivariable calculus. Has Shivendra come? So, you know, you are? We sit down a list. So, linear algebra is something I am sure many of you have learned in your engineering first year or second year, vector spaces and bases and all these things. So, we have to accept that knowledge. I will accept that you know that thing. Without that, no progress can be made even by John Burge, who would be the main lecturer of this course. So, I am here just to push you into this. I am here just wanting to light the gate of a huge building called convex analysis and optimization. So, multivariable calculus is the calculus of more than one variable. The calculus that you learn at school, even in the beginning college, it's just one variable. And multivariable calculus means we have more variables, but many of us possibly do not realize that from our childhood we have actually spoke about multivariable calculus. We had studied function of two variables because before we studied function of one variable. So, you know, when you are having say 5 apples in a box and 3 apples in another box. So, how many apples are there together if you put them in one box? 8. So, what is so instead of 5 I could have put anything in the first box, instead of 3 I could have put anything in the second box. So, first box I could put x, second box I could put y, and the total z is nothing but x plus y. So, this little addition itself is a function of two variables. So, this very basic thing that you learn in the beginning is function of two variables. So, how do we, so this part is also taught in your basic engineering math and basic math courses and physics courses. So, it is very important to know when you study science, what is the nature of science. Can anyone tell me what is the nature of science? So, before we actually start getting into the technicalities of convex sets, we talk about a bit about why you study science. So, anybody having any idea what is the nature of science? I want to really tell you that there is a huge gap. People really do not understand that the nature of science and nature of mathematics are very different. Though we club mathematics in sciences, but it should be actually mathematics, the natural sciences and the sciences and other arts and other arts and literature and other activity. So, can anyone tell me what is the nature of science? You. Anybody else who would like to try, or what science actually is? Western logical. See, in science, what we have is observations. Primarily, science takes in a lot of observation, and using that it it makes a conclusion, and the laws that you see in science, whether Newton's law or whatever you want to say, any law, is actually based on observation and experimentation. So, there is also something called scientific theory, and people say, okay, scientific theories are all vague, etc., etc. No, based on a given observation, if you can explain a phenomena, and if and whatever is the outcome of that theoretical exercise, and that is observed in whatever other experiments you carry out about the phenomena, then the theory is robust. Mathematics does not base itself on observations, though largely the development of mathematics has been very deeply linked with the development of physics, but of natural sciences, but as it grew as a subject, mathematics has its own color actually. But this color was also shown by the Greeks, that mathematics bases itself on certain logical assumptions, which are called axioms. And based on that axioms, whatever you derive is absolutely true. Because what happens in a scientific theory, that if new observations come in about a phenomena, then the current theory either has to be modified or in some cases have to be completely junked. But a mathematical result based on a given system of axioms, once it is established, it is established. While a scientific hypothesis or scientific fact may change. Like for example, what you know about Newton's laws in this macro setting is not true when you go into the world of atoms, right. So, as a result of which there is a difference in thinking. So, mathematical thinking is pretty different than what we are trying to do. उसको बंद कर दो. But okay. But Professor Borge would teach from slides. So, we will start with the concept of line segment. You know, so I have 2 points in Rn. So, here everything what I am talking about Rn, I am drawing them on R2, because my vision would be limited to R2 and R3, right. So, here is a line segment joining these 2 points x, y. So, mathematically the line segment joining x, y is defined like this. It is a collection of all z of the form lambda y plus 1 minus or z lambda of the form 1 minus lambda x, where lambda is lying between 1 and 0. This is basic coordinate geometry basically that you have done in class. And so, what is a convex set? A convex set is a set such that if you take any 2 x and y, any 2 points, this, the word any is there in the convex set, then a line segment joining these 2 points would always lie inside that convex set. So, a set is called convex if I take any 2 points in the set and join them by a line segment. This whole line segment would lie inside that set. That is, this line segment itself would be a subset of this set, and that will be true for any 2 points. Does not matter if I take x dash, y dash, this is for example, if our set is like this, if a set is like this, then you see I show you 2 points x and y, which when joined by a line segment, a part of the line segment is outside the set. Human body is a non-convex set. So, this set is a convex set and this is non-convex. If you can't read the writing, if you think that writing is bad, you can just come forward. So, check whether you agree that human body is a non-convex set. Take a point here, join them, you are out, right. Nature always does not bother about convexity, but you see beehives for example, they are convex in general, but approximately convex, but nature hardly bothers about convexity. Convexity is a very man-made construct. This is a convex set, surface of this table, this is a convex set. So, it is a man-made construct, but they without convexity, there is no other set which you can describe properly. You cannot describe a given non-convex set, but you can describe a convex set. So, what is a convex set? A set C is convex if for any x y in C the line segment joining those 2 points are lying in C. So, now we write down some basic properties of a convex set, which you can try to prove. So, I am giving you 2 convex sets C1 and C2. So, C1 intersects, so these are convex. So, C1 intersection C2 is convex, while C1 union C2 is not convex. Because it's, for example, you take this one and this one. So, this is say C1 and this is C2, you take the union of these two. So, if you take the union of these two, you can easily see that there are 2 points where if I join them by a line segment, part of it is outside. When you have learned set theory, you have always thought about union is something like expressing an addition of 2 sets, but that is really not so correct, but there is another way to define set addition of 2 sets, thinking of those 2 sets C1 and C2 as sets in a vector space Rn. So, this is a class of type of addition called Minkowski addition, named after the famous Hermann Minkowski, who was also Einstein's teacher. So, given 2 convex sets, I am defining their additions as following. It consists of all z of the form x plus y. So, this is a vector addition, x and y are vectors. So, these are n coordinates, this is n coordinates. So, when you, so if x has the coordinates x1, x2, xn and y has the coordinates y1, y2, yn, and x plus y has the coordinates x1 plus x2, y1 plus y2, yx2 plus y2 and so on, xn plus yn, where x is element of A and y is element of B. So, once that is done, we will now try to give you examples of convex sets. So, learning these examples are much more important than anything else. So, first example that I will give is that of an hyperplane. So, we start this as examples of convex sets. So, we will introduce what is called a hyperplane. So, is not convex in general. If you want, I should write this word in general. If it is convex, then one must be a subset of the other. One must be inside the other. If it is not that, not so much. So, hyperplane, the most simple hyperplane that you know is a straight line lying in the plane, Cartesian plane. So, we will just write down the definition. So, hyperplane H consists of all x in Rn such that the inner product of a given vector A with x, so A is fixed, is equal to some B. So, if A is so inner product is nothing but the dot product, same as the dot product. So, if A represents the vector A1, A2 and x is given by x1, x2, now you are in 2 dimensions. So, A here is in, of course, in Rn, because otherwise we cannot have an inner product with the element in Rn, and this is in R. So, by definition of an inner product, it means first coordinate of this is multiplied with this plus second coordinate of this is multiplied with this. This is not an unnatural definition. This is an extension of the very simple idea of multiplication of two numbers, real numbers, into the higher domain. Right, that is all. And this equation means this is equal to B. So, what is this? This is an equation of a straight line. So, those who remember their coordinate geometry would really understand that this is equation of a straight line. Okay. But a hyperplane is a very this hyperplane is a convex set, of course you can prove. So, how would you, if you want to prove that a set is convex, how would you prove that a set is convex? So, you will take say 2 elements from the hyperplane and you make their convex combination, whatever be the lambda between 0 and 1, you make this combination. So, you want to see whether this z lambda is inside this set. If z lambda has to be inside the set H, because any point on the line segment, the whole line segment has to be in this set, then you have to prove that A of z lambda is equal to B. So, what you to do? So, you calculate A of z lambda, which will give you A of lambda x1 plus 1 minus lambda x2 is this comma, of course. So, lambda A of x1 plus 1 by the rules of the inner product. So, we are in real vector spaces. So, the field, whenever we are talking about real numbers, which is the field elements associated with a vector space. So, these are all real numbers. So, we are in Rn is a real vector space, right. Now, this is A of x1 is equal to B because x1 was in H, and A of x2 is equal to B because x2 also is in H. So, you will have lambda B plus 1 minus lambda B, which simplifies to B. So, that means Z lambda belongs to this set. So, and hence this is a convex set, but this set is slightly more. This is not just a convex set, but it is something called an affine set. An affine set is a very particular type of convex set. Maybe I should write it here. So, affine set is a set where not only just the line segment joining these 2 points lie in the set, but the whole line that passes through that point lies in that set. So, if you take a straight line and take 2 points in this line, now the line segment joining these 2 of course lies in this set, but the whole line that passes through it also lies in the set. That is called an affine set. So, come here, tell me.
Actually, x1 and x2 both are different variables.
What both belong to H?
Yeah, and so, if we represent
this is A comma.
So we can take P or P1 here.
P, this is fixed now.
Or for all variables, for all x.
Any x which has to lie in this set has to satisfy this equation, right. So, when you lie, so what is the meaning of a line passing through x y? A line passing through x y is usually denoted like this, is a set of all z lambda of the form lambda x plus 1 minus lambda y, or lambda y plus 1 minus lambda x. Okay. Lambda is the element in real line. That is it. That is the meaning of a line passing through AB, through 2 points. So, here if you look at this equation, when lambda is equal to 0, I get x, and when I put lambda equal to 1, I get y. So, as I vary lambda from 0 to x, I am walking along the straight line from x to y. That is the meaning. And here it does not matter, here you just keep on walking. So, an affine set is a set which not only contains the line segment, but it contains the whole line passing through 2 points x, y. So, A is affine if for any x, y in A, the line segment, the line passing through them is also a subset of A. That is the meaning of an affine set. See, you have to understand the affine set is not a subspace in the sense of linear algebra. Subspace is a subset which of a vector space which is also a vector space itself. So, this hyperplane has a particular structure. It is a translate of a subspace. For example, if you move this line parallelly, there is a time, there will be a point where this will pass through 0. So, it is a translate, you are translating the subspace, any straight line in R2, 2 dimensions passing through 0 is a subspace. So, you are translating this. So, consider this set H naught, which is a set of, this is a subspace X element of Rn, such that A of X is equal to 0. So, this is a subspace. Any subspace of vector space is also convex set. So, while H is not a subspace, so if I put Ax equal to B where B is non-zero, then H is not a subspace. So, take any x naught element of H. So, this would imply A of x naught is equal to B. X naught element of H means this one. So, A of x naught must be equal to B. So, which means I can replace B by this number. So, A of x now is equal to A of x naught. Now, this implies that A of x minus x naught, when you bring this to this side and use the rules of inner product, dot product, you will get this. So, what does it simply show? It simply shows us that x minus x naught is an element of H naught. Because any element of H naught must satisfy this. So, if x minus x naught is satisfying this, it must be in this H naught subspace. Okay. So, then x is an element of x naught plus H naught. So, this is true for any element of H. So, this implies those who have no sum sets. So, this implies that the set H is a subset of x naught plus H naught. So, you have a translate. So, I am essentially telling that this H is a subset of a translate of H naught by an amount x naught. Okay. In fact, we want to show that these are equal. So, for that, take any y which is an element of x naught plus H naught. If you take any element like this, then y can be represented as, because this is an element of this particular set. So, it is represented as x naught. X naught is actually nothing but a singleton set. X naught is a singleton set added to this set. So, it is the same C1 plus C2 thing basically. X naught plus x dash, where x naught is this and x dash is an element of H naught. Now, let us see whether y belongs to H. So, we want to say that any element of this will also belong to H. So, H would be subset of this and this would be subset of H, and so they would be equal. So, let us see what is A of y. A of y is equal to A of x naught plus x dash. Now, A of x naught plus, which is same as A of x dash. Now, you know that A of x naught is B because x naught is already in H. Plus A of x dash is 0 because x dash belongs to H naught. So, this is B plus 0 is B. So, A y is equal to B. So, y is element of H. So, what does it show? It shows that, it simply shows that from here, if I write it from here, it shows that x naught plus H naught is also a subset of H. So, what do we conclude from these two equations? We conclude the following central geometrical fact about a hyperplane, that an hyperplane H is a translate of a subspace. Now, if you look at the plane, two-dimensional plane, and if you just draw a line, you take the two-dimensional plane and you draw a line here, you will see that it divides the plane into two parts. Each part is called a half space, and these half spaces become very, very important in understanding the nature of convex sets. So, we will now define what are half spaces. So, here is a straight line, it divides us. So, this is a straight line or a hyperplane given by the equation Ax equal to b. Now, this set of points is called the upper half space, and this set of points is called the lower half space. The upper half space is given by, so here if I move away from here towards this side, the value of Ax, A inner product x will increase, it will become bigger than b, and if I go below it, it will become lesser than b. So, in this region, you will have all the x's for which A of x is bigger than b, and in the lower half space, that is this part, it will be all elements of Rn which is lesser than b. These sets are convex sets, but remember these sets are not affine sets. Just think about what I have just written. These are convex sets, but these are not affine sets. Another important class of sets is called the polyhedral sets. Polyhedral sets are used heavily in optimization. Rather, optimization thrives on polyhedral sets. This is a very particular type of convex sets, but this is something that you ought to know. I think polyhedrality will also come in Professor John Burge's lecture. So, polyhedral sets are formed by intersection of half spaces. So, here is one straight line creating some half space, here is another straight line creating some another half space, here is another straight line creating some half space. So, now I am looking at the intersection of these half spaces. Upper half space or lower half space does not matter. So, this set P is polyhedral. So, you forget these lines. So, this part only, this bold line that I am making, this is a polyhedral set. See, the set could just keep on progressing, it could be unbounded, it is not that it always has to be bounded by some boundary. So, this is a polyhedral set which is a closed set, but it is not a bounded set basically. So, polyhedral set P is usually represented as x element for those x in Rn for which the following is satisfied Aix. So, we are looking for finite number of half spaces. So, polyhedral sets are intersection of finite number of half spaces. Do not consider infinite number of half spaces, finite only. So, Aix is less than equal to Bi, I want to say M, and Cj x is less than equal to d is bigger than equal to di, dj, j equal to 1 to k. So, these are very general expression of a polyhedral set. I will just give an example which you can very easily understand. It is a very simple thing to understand. So, consider things in R2 now. Now, of course, I will show you how I am representing this x greater than 0 and this greater than 0 in this form. In that inner product form. So, but let me just draw this particular say p tilde. So, you have to be in only in this space where x is greater than equal to 0 and y is greater than equal to 0. That is, you have to remain in the first quadrant, you cannot go to any other quadrant. And then x plus y is equal to 1 is the line passing through 0 1 and 1 0. And then you are only looking at those points which are less than equal to 1, means this line and including this point. So, now how would I express this one in terms in this form? So, let me look at E1, which is the natural basis vector of R2, and E2, sorry, and look at another vector called E, which is 1 1. Then P tilde, I am just removing that side. And P tilde can be written as x y in R2 such that E1 inner product so let us no, just give me a second. Let us write that it consists of all z of this form x y in R2 such that E1 inner product z is greater than equal to 0, E2 inner product z is greater than equal to 0, and E with this E inner product z is less than equal to 1. So, that is how you represent the half spaces. Now, we will come to another important concept called convex combination, right. So, convex combination is just like what we did when we wrote lambda y plus 1 minus lambda x, we were actually doing the convex combination of two vectors. So, if I have more than two vectors, how will I do my convex combination? We will give you some exercise in the second half about convex combinations. And so if I have n elements, so k elements for example, so k vectors x1, x2, xk all are in some convex set C, say, or in Rn if you do not want to say C, whatever you want to mention. So, these are all vectors in Rn. So, their convex combination is an element of the form z lambda, where I write in this form. It is a kind of linear combination, of course, where these lambda k's have the property to be between 1 and 0, and the sum of the lambda i's from that is lambda 1 plus lambda 2 plus lambda k, this is exactly equal to 1, and that is called a this is called a convex combination. This is called a convex combination. So, our exercise that you have to prove in the second half is that every convex set contains its convex combination. If you take a convex set and take any n points and do this convex combination, or any k points and do this convex combination is always going to lie inside that convex set. Now, I will introduce a very important notion, which is a tool, which is an idea, which is has a very important connotation in something called integer programming. That is, where your decision variables become discrete, how you are going to handle the situation. And that is a notion called convex hull. It is called how to convexify a non-convex set. So, if a set is non-convex, what should I add to that set so that set will become convex? So, that is the question. Can I make a non-convex set by adding some more points? Can I make it convex? That is the question. So, that is what we are going to now answer. For example, this is a non-convex set. Say this, we call it S, whatever. So, you know that if I take points here, then also the part of the line segment is outside. So, if I include the points here in the set, so these points also, so if I include these points, basically tangentially, if I include these points, the points for which where this set was becoming non-convex because they were lying outside. And you see, if I have added this part to the set has now become convex. So, you see what I have done, I have tried to pack this given non-convex set into the smallest convex set possible. Of course, I can pack it into a bigger set, but that does not make this a convex set. I want to pack it up in such a way that there is no other space for movement. So, the convex hull of S we will load the notes into the this Google Drive. Convex hull of S is the smallest convex set containing S. So, you see whatever convex set I take, this convex set would become fit in loosely inside it. Only in the smallest one it will fit in tightly. Basically, I can write this as intersection of all S hat, where S hat contains S and S hat is convex. So, this is the convex hull. So, convex hull, as usually we use this symbol convov S. There is a particular way of writing convex hull. Actually, convex hull contains all the convex combination of the elements of a given set. That is a fundamental rule for how you find the convex hull. So, given a set S, the convex hull of S is equal to the following set. So, it contains all possible convex combination. Remember, convex combination of elements means we only consider finite number of elements. In a convex combination, there is never an infinite number of elements. in a convex combination there is never an infinite number of elements. So, it consists of all z of the following form: lambda I xi I is equal to 1 to k say, where k is a natural number and xi is element of S for all I, lambda i's are greater than equal to 0 and summation lambda I is equal to 1 to k is equal to 1. Now, how do you construct this? It is a very difficult thing to construct, because what I am expecting from you is the following. I am expecting that you construct, when you take every possible k is 1, k is 2, k is 3, k is 4, you keep on increasing it, and then you make this convex combination and consider all possible lambda i's which will do this summation lambda i's. So, it is a hugely murky task, and it is a NP hard problem even in computational geometry to construct a convex set even on a plane, right. But if that could have been constructed, a lot of optimization problems would have got simpler. The only simplification of this is that, but it is a huge simplification, it is a huge advantage, it is a huge leap. It is a result by Carathéodory, is a famous Greek mathematician who has huge contributions in the calculus of variations, which is one of the most important parts of optimization. There is a result by Carathéodory, and it is taught in linear algebra, or at least in convex analysis, Carathéodory's theorem. So, in Carathéodory's theorem, what do we learn? Carathéodory says if S is a subset of Rn, then I need not bother with changing this k, I can fix this k and I will use only that number of elements. So, you see huge simplification, huge immediately. It says that then convex hull of S is equal to the set of all x element of Rn such that so z element in Rn such that z is equal to elements of this form I is equal to 1 to n plus 1. So, you now fix your k to n plus 1, you just have to represent with n plus 1 elements. You do not have to say first with 2 elements, then with 3 elements, then with 20 elements, then with 10,000 elements, it is not like that. So, just with n plus 1 elements. So, if I am in 2 dimensions, I will just need 3 elements, right. So, lambda n, obviously lambda is greater than equal to 0 and summation I is equal to 1 to n plus 1 lambda is greater than equal to 0 and xi's are element of S. So, there is a huge simplification, and this result, this Carathéodory's theorem is also used in research till date. When you want to represent convex hull, this is the best way to go about, because if both are varying, that is, if k is also varying, if this k is also if this k is varying and these lambda i's are also varying, then it is very difficult to manage the things. If one is fixed, you can manage the other. Now, we will talk about another special class of summation lambda is equal to 1. Thank you. So, now we will that was true also. Now, we will talk about a very special class of convex sets called cones, rather convex cones. We will talk about convex cones. So, let us look at what is a cone. Cone is an ice cream cone, you see. You take a cone, when you take an ice cream, you have you are inside a cone. So, you can in your mind's eye imagine that cone is starting from that point and then just keep on growing up, right. So, that sort of imagination one has to build it. Mathematics, a large part of your mathematics happens in imagination. So, There is no Euclidean plane in reality. So, what are cones? The most standard definition is the following, that S is a cone if whenever x is an element of S, lambda x is an element of S for all lambda greater than or equal to 0. So, here it simply means it is a cone with a vertex at 0, something like this, say in 2 dimension. So, if you take any x, so what is the meaning of lambda of x? It is nothing but a scalar multiplication of vector. So, lambda of x means either you are stretching the vector or you are shrinking the vector. If lambda is greater than 1, you stretch the vector, make it longer, or if lambda is less than 1, you shrink the vector. So, you can have also, so what I have drawn here is a convex cone, because this is a convex set finally. I can also have a non-convex cone. Speak about cones which are having vertex at some other point S. In this case, the definition will simply change. It will say that S is a cone if S plus lambda x minus S is an element of S for all x which is an element of S and lambda which is greater than or equal to 0. Basically, you have now, instead of 0 as the origin, you have taken another vector as the origin. Now, if I put S equal to 0, I will go back to the same definition. If I put S as the 0 vector here, I will go back to the same definition. A cone which is a convex cone which is convex is called a convex cone. We will give you some exercise about convex cones in the next in your exercise, right. So, just like the convex hull of a set, we can simply now talk about what is called an affine hull of a set, and this will take you to a domain which is I think because of the loss of time we had so whatever would be left tomorrow, because I will do it tomorrow, I will put the slides on. So, we will define what is called an affine hull. So, we have actually 3 lectures to finish up to basics of convex optimization, that we will finish. You do not have to worry much. So, what is called an affine hull? I do not need to tell you the definition now, because once you know what is a convex hull, affine hull is nothing but the smallest affine set which contains a given set. So, for example, I have for example, look at the line segment, just this is the set S. So, what is the affine hull? What is the affine set? Smallest affine set which contains the line. You see, the whole space is an affine set. This is a vector space. Any vector space is an affine set. But what is the smallest affine set which contains this line segment? Affine set, smallest affine set which contains this line segment is the line passing through these 2 endpoints. So, this is the affine hull. But if you have a set like this, What is the smallest affine set which is containing this set? Is a whole space R2, no line, nothing will do. So, this case, if this is my S now, so we write the affine hull of S is actually written as AFF. Affine hull of S is the straight line. But here the affine hull of S is R2. The dimension of a convex set, the dimension of a convex set is the dimension of the affine hull of that set. So, people can ask what is the dimension of a set? See, you know what is the dimension of a vector space, but then what is the dimension of a set? Nobody has defined dimension of sets or dimension of, for us we need just convex sets. So, what is the dimension of a convex set? So, dimension of a convex set is the dimension of the affine hull in which it is contained. But what is the dimension of affine hull? What is the dimension of this affine hull? The dimension of the affine hull, for example, this straight line is the dimension of the subspace whose translate is this affine hull. So, it is a translate of some subspace, but subspace has dimension. So, that subspace, whatever is the dimension, so if you translate this, the dimension does not get changed. A straight line, if you translate, its straight line nature or one dimensional nature remains same. So, all the affine lines which are generated because of this translation would have a dimension 1. So, here is an important definition that one needs to know, that the dimension of a convex set, say I will just talk about convex set, say dimension of a convex set C is that this is convex, is the dimension of affine C. So, in the 10 minutes that we have, we will talk about a very important concept called relative interior. Again, I will go back to this picture. If I take this point, you know the definition of interior of a point in a set or even in real line, that if you take a point and if you take a ball around it, that ball should lie inside the given set. So, interior point means given a point, I should be able to find a ball around that, a spherical ball for example in 3 dimension, so that the ball is completely inside that set. If I take this any point here on this is a convex set actually, it is a line segment, it is a convex set. So, if I take any whatever however small radius, it does not matter, I take a disk, because in R2 my neighborhood is a disk, right. Disk means actually everything inside, not the boundary, but we are just drawing the boundary. Whatever we do, however small the radius of the disk may be, this disk is never contained inside this line, can never be a subset of this line. So, none of the points in the line segment, this set has an interior point, but it looks, because it is a straight line, you see, it looks like a closed line segment, it is a open like a closed interval on a real line. So, it must have an interior point. So, here one defines what is called a relative interior. Relative interior means the following. It means that, okay, it does not have, it does not contain there, I mean it does not. So, but I can always take a, I can always get a delta radius, a ball of delta radius around a given point x bar, if I want to call it a relative interior point. So, that is intersection with the affine hull of this S is a subset of S. So, you see when I take a ball of this radius, a disk of this radius, the intersection of the ball with the affine hull is this part, and this part is a subset of this set. So, then for such points x bar, this x bar is called a relative interior point. Is called a, it is called a relative interior point. Okay. And so, if a set consists of all points which are relative interior points, then the set is called relatively open, and the set of all relative interior points of a set is called the relative interior of the set. So, if I collect all the points which are relative interior points, it is called the relative interior of the set. A very important result of convex analysis is that the relative interior of a convex set is always non-empty. So, the relative interior of a convex set, that is the collection of all relative interior points, is given by this RIC. So, if C is convex, this relative interior is always non-empty. This is a very famous result, but this is not true when you are in infinite dimensions. But we are not getting into infinite dimensions, so we just have to take care of this result. Now, the interesting part is that when affine hull of a given set, say C, convex set is Rn itself, if the affine hull of a given set C is Rn itself, then the relative interior of the set C is nothing but the interior, because now the ball would be inside the set, because the intersection of the ball with Rn is nothing but the ball itself. So, the ball inside would be inside the set. So, the relative interior of the set C is interior of the set C. So, any full dimensional convex set, so if you have an n dimensional convex set or 3 dimensional convex set in a 3 dimensional space, then it must always have an interior. So, with this I will stop the thing, because that will become too much if I start talking about what I have already done, because that would. So, now you, of course, you can define what is called a relative boundary. Now, I expect you to know what is an interior point and what are the basic, say, facts about open sets, closed sets. These are things which you really have to know. You can just check out the Wikipedia. I'll. So, you can define what is called the relative boundary. So, that is nothing but the closure of the set A. From that, if you take out all the relative interior points, so relative boundary of a set A, a convex set A, is this. And important result is that relative interior of the closure of a set A, or convex set A, is the closure of the relative interior of A. And closure of the relative interior of A, so sorry, made a mistake. I did. So, relative interior of the closure of A is same as the relative interior of A, and relative, if you take the relative interior of the closure of A is a convex set, by the way, then this is nothing but the, so relative interior, no, closure of the relative interior of A, then it is nothing but the closure of A. Of course, A is convex, A is convex. So with this I will stop, and tomorrow I will put it on the slides to discuss before I discuss convex functions. We won't have very much left, but something more is there, so we will finish that. Because you don't need too much thing in convex optimization except the very basics. So and that we won't go too much into the proofs. So we will start from here.